Okay, time for these 3D problems. These are the ones that you have to think most about. Not because they're difficult, but because you actually have to read the question and know what's given versus what they're asking for. So in this question, it says if 1,200 centimeters squared of material is available to make a box with a square base and an open top, so that could change per question, find the largest possible volume for the box. So what I need to point out to you here, oops, wrong thing, is that you are given a value for surface area, but you are asked to maximize the volume. So we have two things going on here. We've got surface area and we've got volume, and I'm going to keep them on separate sides of the page. I'm going to do the surface area in red, I'm going to do the volume in blue, and in addition to that, I am going to draw a picture because I want to show off my ability to draw a square-based box. So first of all, I don't actually have to draw a square base, I have to label a square base. So here is my box. And to represent that it has an open top, I'm going to do that to say, okay, I can see into the box. So being a square base means that this is x and this is x, and I have no idea how tall it is, so I'm going to call it a different letter because it doesn't say it's a cube, so I'm going to call that y. And this is what we can build the red surface area equation based on. So surface area is you taking the 5 sides, not 6 because it's open topped, the 5 sides and doing the area of each. So I've got a bottom, and the bottom is x times x, which is x squared. And then I've got the front side, which is x by y. The back is also x by y. The right side is x by y. And the left side is x by y. So that's where you have some thinking to do. And this is all equal to 1,200 centimeters squared. So I can tell it's surface area because it's centimeters squared. So I'm going to make this look a little prettier. 1, 2, 3, 4 of these xy's. And then I'm going to keep reading. So that's as pretty as I can make the surface area formula. It says find the largest possible volume of this box. So volume of a box, regardless of whether it has an open top or it's actually got a top to it, is length times width times height. So I want to maximize this. And the length times width times height is that. So maximize x squared times y. So this kind of reminds me of a number problem where you have two sides of the page and you're trying to minimize or maximize something, and then you've got a different equation over here that you can isolate a letter for. The problem is, in this particular question, isolating a letter here is actually quite a bit more difficult than just taking one thing to one side and being done with it. So in this case, I'm going to try to get that y by itself. So it's going to take me a couple of steps. Step 1, I'll take the x squared across the equal sign and subtract it. And step 2, you can do this in a couple of different ways. I'm going to do it this way. I am going to divide by 4x so that I'm left with y, which means I'm going to divide this side by 4x, but I'm going to do it twice, once for each term. So if there was 5 terms, I'd divide it 5 times on the right-hand side. So now I'm going to clean this up. So y equals 1,200 over 4x minus x squared over 4x, and I can do even better than that. So 1,200 divided by 4 is 300, and I'll have an x in the denominator minus, I'll have a single x in the numerator and a 4 in the denominator. And this is what I'm going to put in here. So this now becomes x squared times 300 over x minus x over 4. And I don't want to take the derivative of this because if this doesn't have an exponent, it's probably pretty wise to multiply that in. And then you don't have to do the product rule or the quotient rule or any combo rule. So 300 x squared over x is my first thing. And then minus x cubed over 4. So if I'm taking the derivative, just to make this look a little prettier, I can knock an x out of each term here, and this one stays the same. And now I can take the derivative. So I'm going to tell you I'm taking the derivative with my little tick. Derivative of 300x is 300, and the derivative of this is 3x squared still over 4. And I have to equal that to 0. Otherwise, everything from that point on isn't mathematically sound. And because I've got two chunks of information here, I've got an x squared. I don't particularly want to factor this. I don't have an x. I'm not going to use the quadratic formula. I'm going to take the 3x squared over to the left and make it positive, equals 300, and I'm going to put that 300 over 1 so I can cross multiply. So if I cross in this direction, 3x squared times 1, and if I cross in this direction, it's 1200. Isolate x. Divide by 3, divide by 3. X squared is equal to 400. X will equal to plus or minus the square root of 400. But what did we let x be? We let x be the side of a box. Two sides of a box, actually. So when I take the square root of 400, and I get 20, I'm not writing down the negative. It doesn't even make sense for this question. If it was a number question and we ended up with plus and minus 20, that would be fine. You would have to accept both. But this is a question about the sides of boxes. So now that I have my x is equal to 20, I know that according to my picture, the base is 20 by 20, 20 by 20 centimeters. I just need to know how tall this is, and that's y. And I have a little phrase, equation for y right here. So I'm going to take that 20 and I'm going to put it in for all the x's. Y equals 15 minus 5, which is 10. So, my therefore statement. Therefore, the base is 20 centimeters by 20 centimeters, and the box is 10 centimeters tall. And yes, you must be specific, because if it was 20 by 10, then it doesn't have a square base, and the top would change as to which dimensions it has. So we're done that question. So you have to think about this kind of stuff more so than you do when you're talking about number problems or money problems, or what did we do earlier? We did travel problems, which were all based on Pythagorean theorem. So this one's going to change up a bit. So hand cramp, rest time. Here is the next one. I'm going to pause for a moment. So do you see how this one's a bit different? It's a couple of things. Oh, crap. Couple of things. Number one is I gave you the information in a backwards order. This is volume. And you can tell it's volume because it's got meters cubed. And then we want to minimize most economical container, minimize the cost. And the cost is based on surface area. So number one, I reversed volume and surface area in this question. And second of all, I brought in costs, which is actually what happens in real life, because you do want to minimize your costs when you're building things. So I'm going to start again by drawing a picture. So same box, only this time, because of the first little bit of this, it says closed rectangular storage container. So that means all the sides are contained. So this, I'm not going to color it in because it actually counts. It's got a lid on it. So it says the length of the base is twice the width. So I'm going to make this my width, and I'll make this the length of the base, which is twice the width. And then this is unknown, so you get to call it another letter. And dig out the red pen. Volume is length times width times height, so it's actually got a formula. So that's 2x times x times y. And volume is 10 meters cubed, right here. So that's 10 equals 2x squared y. And now I can move on to my blue stuff. So I'm going to start with surface area. Yeah, I know there's costs. I'm going to start with surface area. So the bottom is 2x by x, so 2x squared. Just scribbling that underneath it. Plus, that makes the top 2x squared. And this right side is 2xy. And that makes the left side 2xy. And the front is x by y. And the back will also be x by y. So now you know why I wrote base. All right, so I'd love to clean this up, but unfortunately I see two different costs, so I have to pay attention. So my next line is going to be cost. So it says material for the base costs $8. The sides and top cost $6 per meter squared for both of them. So the base is $8. And then everything else is $6. So the 2x squared is $6. And now I'm going to collect like terms. 2xy, one more, makes 6xy's. And then I can make this look better. So 16x squared plus 12x squared plus 36xy. So I want to minimize 28x squared plus 36xy. So this is the expression that explains what the cost is, depending on the lengths of each of the sides. Now, the problem with taking the derivative of this is that you don't know how to take the derivative of two different letters. So you've got x's and y's on this side. And it would be great if you could think about implicit differentiation, which, yeah, you could take it if you have two different letters, but technically there's like a third over here. So this isn't even an x or a y. So that's where this red information comes in, meaning I have to isolate one of the letters. So you can either choose to isolate the x or the y, and because the y has no exponents, it's way easier. So y left behind will be 10 over 2x squared, which is 5, and the x squared stays in the denominator. And now I can put this in here. And this is all before I'm taking the derivative. You have to take the derivative at some point because this is a maximum minimum question. So I'm just being super careful and writing down all my steps. So I need to know what 36 times 5 is. 180. So this is plus 180x over x squared, which is 180 over x. And I don't want to take the derivative of that using the quotient rule. So I'm going to do this. X to the negative 1. And now I can take the derivative. See? Taking the derivative. 56x to the 1, drop the negative 1 onto the 180, so minus 180x to the 1 less is negative 2. Make that equal 0 because that's what you do for all max-min questions. And then I'm going to put this back to normal. And this isn't quadratic, but it's set up the same way as this one was, meaning we've got two things that could be fractions that you can situate on either side of the equal sign. So I'm going to do that. So I'm going to take the negative 180 over x squared, and I'm going to put it as a positive on the left, and then 56x over 1 on the right, and then cross multiply. So 56x cubed equals 180. Divided by 56, divided by 56, that means x cubed will be divide by 2, divide by 2, and I need to cube root, which does not require a plus minus sign. We get that. So once I figure out this quantity, I will have this side. I can then double it to find this side, and I can put the x value in here to find the y side. So it all hinges on me being able to figure that out. So calculator. So if you prefer, maybe if I prefer, I'm going to take the 180 divided by 56 just in case I reduced and screwed up. There we go. And then I'm going to cube root that. And I get 1.4758. So I'm going to say 1.48. And that means that I'm going to need 2x for another one of the sides. And hold on, I'm not going to do this until I find out what the question asks. Remember that rereading the question thing? Oh, it does say find the dimensions. So I am going to need that. So that's 2 times 1.48, which is 2.96. And finally, 1.48 in there. Five divided by 1.48 squared equals 2.28. So let's answer that question first before I forget to. So therefore, the base is, and yes, this matters because the base was more expensive, and it is 2.28 tall. Now, I left some blanks because I can't remember what the units were. Meters. So the other question after I fill in meters is, what is the cost of materials for the most economical container? So the cost formula before we took the derivative was here or here or here or here. I'm going to use that one, and the reason I'm going to use that one is it's the cleanest version, and also it doesn't have this silly -1 business. So first of all, meters, meters, meters. X is 1.48. So 28 times 1.48 squared plus 180 over 1.48 equals. Remember, this is dollars and cents. So 28 times 1.48 squared equals, add 180 divided by 1.48 equals, and I get 182.95. So all the other decimals don't matter because this is money. Therefore, the minimum cost is $182.95. So we answered everything there, and you do have to really concentrate on what it is that you're being asked for. So it's not as much of a routine as some of the other questions. So we've got one last question here, which is this one. This is my favorite. I wish I were in front of you so I could show you my demo, but I'm going to take a little hand cramp break again, and I'll be back. Pause. Okay, I really do like this question. I know that makes me a geek. I'm going to draw a picture. So, I'm going to read the question. Then I'm going to draw a picture. A box with an open top, so there we are without a lid again, is to be constructed from a square piece of cardboard 3 feet wide by cutting out a square from each corner and bending up the sides. Find the largest volume that such a box can have. So this time we aren't even given surface area, and we're being asked, maybe I need my tablet instead of my mouse pad. We're asked to, is my color off? We're being asked to maximize the volume. So at some point in blue, which was my derivative side, I want volumes length times width times height. But first of all, I have to draw my picture. So it says that we had a piece of cardboard that's 3 feet wide. And it's a square piece of cardboard. So that makes it 3 feet this way and 3 feet this way. And what happens is, it says a square is cut out from each corner. So we're hacking out that square. We're hacking out that square. And we're hacking out that square. And we're hacking out that square. And because we don't know what the dimension of the square is, but we know it's a square, all these little pieces have a side of X. Now, you don't need to put them on. You could put the little ticks on, but I'm just finding it easier to do that. So what happens is you bend up this side here, and it becomes the front of your box, which for me I'm going to draw more like a tray. And then you bend up this side here, and it becomes the side. And you do that all the way around. And you end up with that. So we need to figure out what the dimensions are. Well, I hope you understand that when you fold this side up, this side is X, and this side is X, and this side is X, and this side is X. So we actually have a height of X all the way around this box. And if you fold this side up, so it's just this chunk right here, then it's 3 feet, but we hacked off an x over here and an x over here, so it's 3 minus 2x. And then this one also, only because it was a square, what used to be 3 feet, but we hacked off an x on each side there as well. So now we have the length, the width, and the height. And you can multiply these in any order you prefer. So I'm going to multiply them in this order. And you'll notice that I don't need a let statement, and I didn't even need the surface area. So I'm going to multiply this out. I'm going to FOIL first. 3 times 3, 3 times 2x, 2x times 3, 2x times 2x. Multiply the x in, because I do not want to do the product rule if I don't have to. And this is what I want to maximize. So 4x cubed minus 12x cubed, 12x squared plus 9x. And take the derivative. See, derivative. 12x squared minus 24x plus 9. I am not 100% sure that that is factorable. It is a quadratic. I'm thankful that there's no fractions, but I don't think that's factorable, so I am going to dig out the quadratic formula. So x equals negative b plus minus root b squared minus 4ac all over 2a. A is 12, b negative 24, c positive 9. So negative 24 is 24 plus minus negative 24 squared minus 4ac over 2a. I'll be a little upset if I do all this and come up with some nice numbers, because I don't really like doing the quadratic formula. So it doesn't matter if I take 24 or negative 24 and square it, and then minus 4 times 12 times 9 equals, okay, it was factorable. How do I know? Because that's a perfect square. I can actually take the square root of 144 nicely. Damn. So x equals 24 plus 12 is 36 over 24. So x is equal to 1.5. And 24 minus 12 is 12 over 24 is equal to 0.5. So both of these can't be answers. And if one was negative, it'd be easy to annihilate it, but one of them is not negative, one of them is 1.5, and the other is 0.5. So we have to figure out which one's acceptable. And to be honest, all I need to do to show you this is have this much of my diagram. So I've got both the sides, both of them are 3 minus 2x. If they were different, you would have to figure it out for both of them to make sure that both of them worked. But if I put 1.5 in here, 2 times 1.5 is 3, 3 minus 3 is 0, so I've got a side length of 0. So anytime you get a side length that is 0 or negative, you can't accept it. So that means 1.5 makes no sense as the square side that we cut out of the original piece of cardboard. 0.5 totally works. 2 times 0.5 is 1, 3 minus 1 is 2, that's all good. Same thing here because it was the same one. So this is actually our answer. And I don't know if you remember this from logarithms, but this answer is just fine. But for this word problem, it is extraneous. So we don't accept it. So now I have to go back and read the question, like always. So it says, find the largest volume that such a box can have. So our largest volume is this, or this, or this, or this, not this one. And it doesn't really matter which one you pick. I'm actually going to pick none of them. I am going to put that this is 0.5 because we just figured out that the acceptable x is 0.5. And this is 3 minus 2 times 0.5, which is 3 minus 1, which is 2. And this one's also 2 because it's exactly the same calculation. So my volume, which is length times width times height, is 2 times 2 times 0.5. So that ends up being 2. Ooh, it's feet. Feet, volume is cubed. So back to the original question to reread it one last time. Find the largest volume. Therefore, the max volume is 2, and you can write feet cubed if you want. But just to snazz things up, I'm going to say cubic feet so you know that that's a thing if you ever see it. So, you know the drill. This is funny. Box questions are in that booklet, so number 4, number 6 to 10. The booklet is on the Google Google site, and if you're in the class, you actually have it. So that is all for box questions. We'll come back and do one more type, and that is the field and poster problems. Stop.